Hello, we are in lecture 3A, part 2 of Chemical Engineering Thermodynamics 1 lecture series. In part 1 of the lecture 3A, we discussed about equation of state, which is a relationship between pressure, volume, and temperature of a substance or compound. And toward the end of the lecture 3A, I discussed about charge, the PV charge and PT charge, so that you understand the relationship between pressure, temperature, volume, as well as the change of state from one state to another. For this video, I will give you examples how to read data from the very important table. The table is called steam table. Basically, it's a result or data collection of data for steam at various conditions. If you recall the chart, the pressure volume chart, I told you from the last video that the isotherm is discontinuous, so it is very difficult to represent data, PVT data, using single equation to get correct information. Okay, it is very hard to get one equation to effectively predict all data. So in the old days, people create table to contain data, so the data in the table are relatively correct. You can pick up the data from the specific condition and use it correctly. The data that we use mostly would be data about steam, because steam is used widely in the industry. We use water a lot in the industry, either as a cooling water or as steam for heating applications. Okay. The reason that we use water is that water is relatively inert. It is available with very cheap price. You can find water relatively easily. And also, water has very high heat capacity. So if we want to convey heat from one point to another or transfer one certain amount of heat, water would be a very good medium. So as I said, because of the complication in the creating equation that can represent the data correctly, sometimes it is more convenient to read the data out of the table directly. And the data for steam are listed in what we call steam table. For steam table, there are two kinds of steam table. Okay. The first one is called saturated steam table, and the second one is called superheated steam table. Basically, saturated steam is the condition when steam exists in the equilibrium between vapor and liquid. In other words, whenever we see the word saturated, it means that right now in the system there are two phases, liquid and vapor together. On the other hand, the word superheated means that the steam is in the condition of vapor only. Okay? If you recall this chart or this diagram, this is pressure volume diagram. The dominant feature of PV graph would be this dome. The condition inside this dome means that your system would have two phases together, vapor and liquid together. On the right hand side of the dome, there will be single phase of vapor only. Okay. For the yellow area, where we have liquid and vapor together, this yellow area is called saturated steam. Okay. The vapor part is called saturated steam or saturated vapor, and the liquid part will be saturated water or saturated liquid. Outside this area, the area highlighted in green, we only have vapor only. In this case, it is called superheated steam. Okay, so there are two kinds of table. The table associated with the yellow area is called saturated steam table, and for the green area you can find the data in the superheated steam table. The data that I'm showing right now is saturated steam table. It's indicated here, and the feature of this saturated steam table is that the data are represented as rows, a series of rows, because under this yellow area there are two phases, one single component, so therefore the degree of freedom is 1. So you can specify only one parameters, and then the rest of the variables can be obtained theoretically. So in this case, the steam table, the data are listed according to temperature. You can see the temperature on the left hand side column. Okay, so if I use this table is also at higher temperature. Okay, so if I pick the temperature of 100 degrees Celsius, this is the variable that I identify, the parameter that I identify, temperature. Theoretically, according to the degree of freedom, because degree of freedom is only 1, therefore for knowing only one variable, it means that the rest of the variables are supposedly known. Okay, the way to read the table is going to the right hand side. The whole rows belongs to the same condition. Okay, so the whole row represents the single state of the system. Alright, for instance, if I draw a picture, as long as you are considering saturated steam, it means that in your system there must be two phases, liquid and vapor together. Okay, so as I specify temperature to be 100 degrees Celsius, so temperature is here, then if you read from the table, 100 degrees Celsius corresponds to pressure of 101.33 kilopascal. Okay, so this pressure can be identified right after you identify or you specify the temperature. So the pressure of the system supposed to be 101.33 kilopascal. Okay, and from this picture, because the piston is under equilibrium, the pressure outside and pressure inside must be equal. Okay, for the saturated steam table, if you look at the data, they are listed as shown in column, and there are 4 groups of data: specific volume, internal energy, enthalpy, and entropy. Okay, for each group there are 3 columns. The column saturated liquid means that the data underneath this column belongs to liquid phase within the system. For the saturated vapor, the data belongs to the vapor part in the system. For instance, if we look at this picture, the liquid here supposed to have specific volume of 1.044 cubic meter per gram, listed underneath this column labeled saturated liquid. You go down until you meet the row that we specified. This number belongs to liquid part. Okay, we can get the density of the liquid here by inversing this number. On the other hand, for the vapor part, you can just look up for the number underneath the column labeled sat vapor. Okay, and you can see that the number is 1,000 times larger than liquid. Whenever you have evaporation of liquid, the volume expands about 1,000 times. The difference between these two numbers if you plug it in, if you punch in the into the calculator, you get the difference of 1672. Okay, you just take 1673 subtracted by 1.044, you get this number. It means that for 1 gram of liquid water, if total evaporation takes place, the volume would expand by this much. Okay, and if you look closely, this number is the same number as this number. Okay, and this number is listed underneath the column labeled evaporation. So this evap stands for evaporation. So anything in the evaporation column means that it is the difference between vapor and liquid. Okay. Similarly, underneath enthalpy columns, if you look for the saturated liquid part, the enthalpy can be listed at 419.1 kilojoule per kilogram. If you look underneath the sat vapor part, you get enthalpy of vapor to be 2676 kilojoule per kilogram. The difference here is essentially listed underneath the evaporation column. Okay. Now, if we consider the saturated liquid and saturated vapor under the same pressure, the pressure of 101.33. So if we consider the change from liquid to vapor at this pressure, we can consider that the process is constant pressure. And for constant pressure process, the change in enthalpy would equal to heat applied to the system. So heat is equal to delta H in this case. Okay, so if you take delta H, or if you take enthalpy of sat vapor subtracted by enthalpy of sat liquid, then that would be amount of heat required to evaporate that water into steam. Okay, so in this case, the difference is 2256.9 kilojoule. It is heat required to evaporate 1 kilogram of liquid water into steam. Okay, this number, the number underneath this evaporation column, can also be called latent heat of vaporization. Okay, so you can see that the steam table can also give you the data regarding latent heat of vaporization, and latent heat of vaporization is changing with respect to temperature or pressure. Okay, in similar manner, you can read data regarding internal energy or entropy. If you are interested in using first law for closed system with constant volume, the data for internal energy might be important. On the other hand, if you're dealing with second law of thermodynamics, you may have to look it up for entropy. Now, if I change the condition, let's say if I lower the pressure from 101 to 40.19, okay, what would be the data for this condition as long as the system remains at saturated point? So basically you just look for this pressure. Okay, pressure is listed here underneath this column, so you just look underneath this column for 40.19 up here. Once you can identify this variable, because the degree of freedom is only 1, the rest of the variables can be read from the table right away. So you move everything upward to this point, then you can get the volume, you can get enthalpy right away. Temperature would be 76 degrees Celsius from here, and the number can be listed as shown here. Alright, and then you can see the change in enthalpy of vaporization or latent heat of vaporization is also a function of temperature or pressure. Now, if I vaporize all the liquid water into single phase of vapor, then the system is no longer saturated. This is called superheated steam. Then you need to change the table. This is superheated steam table. Okay, the feature of superheated steam table, you can see the column here, a temperature, and then rows a bunch of pressure. Alright, because we have the single phase, single component system, and degree of freedom is 2. Therefore, we need to identify both temperature and pressure before we can read out all the rest of the data from the table. Pressure is listed here, and this is temperature. So if you pick the pressure and temperature, let's say if you specify the pressure of your system to be 8400 kilopascal and temperature would be 380 degrees Celsius, you can read out the specified pressure and specified temperature from here, and then project that into the table. The group of the data here would be your system. Okay, the way to read the data corresponds to list of variables over here. Okay, so the first one is volume, then internal energy, enthalpy, and entropy. Okay, so if we are interested in enthalpy, right now we can read the number here, 3074.8 kilojoule per kilogram as an entropy of this superheated steam. Another feature for the superheated steam table is this. When you draw the line to divide the table into two parts, okay, the left hand side of this blue line represents saturated steam, while the right hand side describes superheated steam. Okay, you can see the word sat here and there. So that means you can use only superheated steam table for the information regarding saturated steam table as well. You don't need to change the table at all actually. If I draw a system, let's say you focus on the pressure of 8400 kilopascal, okay, at 380 degrees Celsius the steam becomes superheated steam. Okay, it looks like this. If under the same pressure, but I would like the steam to be saturated, then the temperature must be lower than 380. Okay, what should be the temperature? If I specify the pressure to be 8400 kilopascal here, what should be the temperature? The temperature in this system, when we have both liquid and vapor together, sometimes we call this temperature to be the boiling point. Okay, what would be the boiling point? You can also read it out from the steam table. The number of the temperature is listed here within the parenthesis underneath the pressure. On top of the column it is stated here as temperature of saturation. Okay, so that means the temperature now is 298.39 degrees Celsius. As you can see that this temperature is lower than 380. In other words, you may say that as long as temperature is 298.39, there are two phases, vapor and liquid together. If you heat it up under the constant pressure, whenever the temperature rises beyond this point, then you have only single phase, and that single phase is called superheated steam. Okay. From the data, information regarding liquid under saturated condition will be listed underneath this sat liquid column. Okay, so volume, internal energy, enthalpy, and entropy. On the other hand, for volume, for vapor, you can read the information from the data underneath the sat vapor column. Let's do some example. Okay, so example is, if I want to heat saturated vapor at this pressure to 380 degrees Celsius under constant pressure, how much heat would be required? The word saturated vapor means that initially there must be two phases, okay, but we are emphasized on vapor. So we are moving from vapor in this condition to this condition. Graphically, I can draw a picture like this. So the word saturated means two phases, okay, but right now we emphasize on vapor. You have to notice that whenever we talk about saturated state, it does not tell how much vapor or how much liquid we have in the system. Okay, generally it will be defined by the word quality. Okay, the higher the quality, the higher the vapor fraction. The lower the quality, the lower the vapor fraction. Okay, but whenever in general people would say saturated vapor, by customary they feel that it is taken that whenever we call saturated vapor, it means that majority of the water inside the system becomes vapor. So that means the word saturated vapor means the vapor with the quality approaching 1. Okay, so graphically I can say that the amount of liquid in the system is so small that it is negligible. Okay, properties of the whole system is just like properties of the saturated vapor alone. Okay, but in order to make it complete, you need to put one small drop of liquid in there so that there are two phases together for the word saturated. So in this case, pressure is 8400. Temperature can be read from this number, okay, and then enthalpy can be read from this box, because right now we only have saturated vapor, or majority of the system is saturated vapor, and enthalpy can be read from here. Okay, you heat it up until you get superheated steam, because how do we know that at this state it is superheated? We can look from the temperature. That temperature here, 380, is higher than the boiling point of water. Okay, so when temperature is higher, we only have vapor left. Okay, so whenever we have only vapor, we have to look from this side of the superheated steam table. Okay, so under the same pressure, the temperature is specified to be 380. So when you look from the top here, look for 380 as a temperature of our system. Look down until you meet the line here for the pressure of 8400. You can read the enthalpy to be this number. Okay, so at constant pressure, heat would be the delta H. So heat is equal to delta H for constant pressure system, and delta H is essentially H2 subtracted by H1. By punching in the number, you get this amount of energy or amount of heat required for this process. Okay, noted here that the number is about 300 kilojoule per kilogram. What about if I change one word from vapor to liquid? What will be changed? Okay, now we are looking for saturated liquid. It is still saturated. It means there are still two phases within the system. But now we are focused on liquid part. So you can say that mostly it would be liquid, and then only one single bubble of vapor are inside your system. Okay, so instead of looking from this part of the table, now we have to move to the saturated liquid part. Okay, temperature still remains the same. Okay, it is still at boiling, but it is just initial state of the boiling. The quality of this system will be very low, approaching zero, no vapor, almost no vapor at all. So quality is approaching zero. Then from the table you can read enthalpy. Enthalpy would be here as 36.1 kilojoule per kilogram. The process takes place under constant pressure, so therefore heat would be delta H, and just taking H2 subtracted by H1, you get the number. But this time the number is about 1,000. It's in order of 1,000, so it is much higher than previously. Okay, because right now, in order to convert liquid water into pure vapor, it requires latent heat in addition to sensible heat. Previously we just need sensible heat, but now we also need latent heat in addition to sensible heat, and you know that latent heat is much larger than sensible heat. Okay, so this is the way that we can read the information from the table. Now the example that I shown you basically under constant pressure, but what would be the way if the pressure is not constant? Basically it would be the same. You just read from different condition and subtract to get delta H. But now when pressure is not constant, delta H is no longer equal to Q. In order to identify or calculate heat required, now you need first law. Okay, so first law would be delta U equal to Q plus W for closed system. In order to find Q, you need to calculate delta U and W together. Delta U can be read out from the table directly. Okay. One more thing that I need to emphasize for the steam table. Generally, it is known that enthalpy, internal energy, and entropy does not have absolute value. Okay, we can only tell that from one state to another, the enthalpy change is changing by how much. Okay, we cannot say that at this particular state the enthalpy is this much. But in the table, as you can see, enthalpy are listed as absolute number. Okay, just like this, it is said that at this condition enthalpy is this number, 74.8 kilojoule per kilogram. This is something that we need to understand. In steam table, the number here is refer to the reference state. Okay, basically it is stated that for steam table, steam at this condition has enthalpy this much higher than steam at reference state. Okay, and the reference state of all steam table is usually the triple point of water. Okay, water has triple point at temperature around 0 degrees Celsius and pressure a little bit less than 1 atm. For steam table, it would be stated that water at triple point would have enthalpy of 0. Okay, so water at other conditions would have the number as absolute number, the number of enthalpy as absolute number. But you have to understand that that number is essentially the enthalpy change with respect to the reference point or with respect to the value at triple point. Okay, but anyway, as long as you use the data of enthalpy for all conditions in your condition, or in all conditions in your calculation from the same table, it doesn't matter whether the data is relative number or absolute number, because you use the same reference point. So enthalpy of reference point would be cancelled out anyway. Okay, so for this particular video clip, I show you the way to read data from steam table. Okay, and along the way I describe the word saturated. Okay, let you know about saturated vapor, saturated liquid, and superheated vapor. Oh, by the way, if liquid has temperature lower than the boiling point, that liquid is called subcooled liquid. Okay, so the good thing about steam table is that the data is very accurate. The number is quite accurate number, so it is better in terms of accuracy for the calculation, but it is not convenient to use at all. If you have to integrate the equation, let's say we plug it in there to calculate delta U and plug delta U to calculate heat or work. If integration is required or differentiation is required, it is not convenient to use data from table. It is more convenient to use equation. Okay, so next lecture we will describe how to represent set of data by using equation, but you have to keep in mind that using equation you sacrifice some accuracy for some certain condition. Okay, so this is it for this video. Thank you for watching.